Welcome back. So now we're going to be using direct substitution with trig functions. So let C be a real number in the domain of the given trig function. So long as the value that x is approaching is a number, real number, and it's in the domain of the function, you can use substitution as well. So you can use direct substitution with trig functions too. And I have this in your notes. All right, so these functions, tangent x, secant x, cotangent x, cosecant x, those are not continuous functions. They all have vertical asymptotes. However, so long as the value x is approaching is not one of those vertical asymptotes, you can just substitute in. All right, so we want to find the limit as x approaches 0, 1 plus sine x divided by cosine x. All right, so here we look at the graph. It looks, if we look from, so we're looking as x approaches 0 right here. So as x approaches 0 from the left and as x approaches 0 from the right, it looks like our limit exists and it's equal to 1. Let's confirm that analytically. So when we say, when we're confirming it analytically, we're going to do something algebraic to find our limit. In this case, let's use direct substitution. We have no reason to believe we shouldn't use direct substitution. So we have the limit of 1 plus sine x divided by cosine x as x approaches 0. All right, so I've got 1 plus sine 0 divided by cosine 0. And we have sine and cosine, by the way. Oops, I said 0, but I wrote x. Sine and cosine are both continuous everywhere. Let me fix that. And then we will quickly evaluate it because this is really super easy. There we are. All right, so we have 1 plus, well, sine of 0, that is 0 because sine is y. And cosine of 0, that's x. That's x. That's 1. That's 1. I just keep wanting to make that an x. 1. So that would be 1. So there are analytic results confirm our graphical results. And indeed, our limit is 1. All right, so when you can substitute, go ahead and substitute. Well, look at what you do when you can't substitute in a later lesson. All right, so here we have the limit of tangent x as x approaches 0. Tangent is continuous at 0. All right, so we have tangent of 0. So now if you forget what tangent is, you remember that tangent is, I should really write, I can't take the tangent of nothing. So tangent x is equal to sine x divided by cosine x. Right? So if I have tangent 0, that's going to be sine 0 divided by cosine 0. And so that's 0 divided by 1, or 0. So just in case you forgot. There I am, done with that one. All right, so now we're finding the limit of x times cosine x as x approaches pi. No reason we can't substitute in. We've got two continuous functions there. All right, so that's going to be pi times cosine pi. Well, if you have any trouble remembering that. All right, so pi is right here. All right, so what's that point equal to? Well, that would be negative 1, 0. And so cosine, right, is the y value. By the way, r, the radius, is always 1 there. Right? So our cosine would just be negative 1 divided by 1, or negative 1. So our the value of our limit here is going to be pi times negative 1, or negative pi. And then the last one. So the limit of sine squared x as x approaches 0. By the way, that's the same as saying this. The limit of sine x all squared as x approaches 0. So now we can use our limit properties. So we have, and so now I can just plug in, right? And evaluate sine x and then square it, right? So this would be the same as sine of 0 all squared. Well, we know sine of 0 is 0, and if you square it, it's still 0. Right? So there you go. Sometimes it's easier just to think of what's sine of that value and then square that value. Okay? So we've evaluated these three. So when you can substitute, it's just that easy. All right, we're going to use direct substitution. So we have the limit of sine squared x plus 1 divided by cosine x as x approaches pi fourths. All right, so I already have my equals there. That's going to be equal to, so I can, there's no reason I can't substitute in. Everything here is continuous, right? So, and it's continuous everywhere, so it has to be continuous at pi fourths. Sine is continuous, 1 is continuous, and so is cosine. All right, so technically 1 is a horizontal line. Right? So this would be sine pi fourths. Now this is a nice example where, think of it like that, right? Find sine pi fourths and then square that value. Plus 1 divided by cosine pi fourths. And so now let's draw a reference angle. So pi fourths, that's in the first quadrant. Right? That's going to split that quadrant in half, right? Because pi fourths is the same as 45 degrees. It's our 45, 45, 90 right triangle, right? And so we have opposite. So here's our angle. Opposite is going to be 1. Adjacent is going to be 1, and the hypotenuse is the square root of 2. And this is the one time where cosine and sine are the exact same thing, right? It's 1 divided by the square root of 2, or square root of 2 over 2. And we're going to use square root of 2 over 2. And so it's equal to, we have the square root of 2, although I guess in this case, it really wouldn't have mattered much if I used 1 divided by the square root of 2. But we'll just leave it this way. All right, so I have the square root of 2 divided by 2. All squared, so you can see why it would be nicer to think of sine squared x in this case as sine x all squared, plus 1 divided by the square root of 2 divided by 2. Right, so that's going to be a square root of 2 divided by 2 all squared is now going to be 2 fourths plus 1 divided by the square root of 2 divided by 2. All right, so let's rewrite this. 2 fourths is the same as a half. Right, so a half plus 1, that's 3 halves. Divided by the square root of 2 divided by 2. Well, dividing by a fraction is the same as multiplying by the reciprocal. By the way, there was no reason here for me to multiply by a least common denominator because it was easy enough to simplify out. This is 3 halves times 2 divided by the square root of 2. So those 2's will cancel. Final answer, 3 square roots of 2, or we could think of this as 3 square roots of 2 divided by 2. It's an easy enough one to rationalize. We should probably just rationalize it. All right, so we had a few steps here, but they were pretty easy steps. Okay. So direct substitution works very nicely with our trig functions. All right, so here we have another one. We have the limit of cotangent x secant squared x as x approaches 5 pi 6. And we can just use direct substitution on this one. Even though neither of these are continuous functions, 5 pi 6 is not where they have a vertical asymptote. And if you weren't sure, what would be the worst thing that happens? You plug it in, and you evaluate, and you go, whoops, that didn't work. Then you do something else. All right, so that would be equal to, so I already have my limit statement written. I'm not going to write it again. And so I'm going to plug in. So I'm going to have cotangent 5 pi 6 divided by, and I can think of this in denominator as secant 5 pi 6 all squared. Right, that has exact same meaning. All right, so reference triangle. Well, we saw 5 pi 6 just a little while ago. It's in the second quadrant, right? And so my angle there is pi 6. Opposite pi 6 is a negative square root of 3. It's negative in that quadrant, and this is going to be 2. All right, so cotangent, that is the adjacent divided by the opposite. All right, so that's just going to be negative square root of 3 divided by 1, or just negative square root of 3. So this is going to be equal to negative square root of 3 divided by, all right, so secant, maybe I should write this over here. So cotangent, as a reminder, is the adjacent divided by the opposite. So in this case, it was negative square root of 3 divided by 1. And then secant, that's the inverse of cosine. So, and I really shouldn't write, that's actually bad. Shouldn't write cotangent equals. Got to take cotangent of an angle. Even though you know what I meant, I should really say cotangent 5 pi 6. And then we have secant 5 pi 6. So inverse of cosine, that's going to be hypotenuse divided by adjacent. So that's going to be, I'm going to put the negative in the numerator, negative 2 square roots of 3. Or I can call that negative 2 square roots of 3 divided by 3. And it's not going to make that much of a difference which way we choose to deal with it. Quite honestly, maybe we'll just leave it unsimplified, unrationalized. The negative 2 square roots of 3, less numbers until we finish up. Yeah, let's just leave it like that, because I think the square root is going to help us a lot. All right, so here we have, I'm just going to do negative 2 square roots of 3. And the heck with rationalizing it. And we're squaring it all, so that's going to get better. And go sideways here. So we have negative square root of 3 divided by, that's now going to be positive 4 and 4/3. Right? So the square root of 3 is, and square root of 3 squared is just 3. And now we're just multiplied by the reciprocal. Right? So that's going to be equal to negative 3 square roots of 3 divided by 4. Right? When you divide by a fraction and we're dividing by 4/3, that's the same as multiplying by the reciprocal. And there we go. That one's all done. And that's it for this lesson. So after properties of limits, which was a very long lesson, you get a very short lesson, and that was limits of trig functions. Well, bye for now.